Hi everyone, welcome back. We're now getting into advanced counting techniques. Our first topic is recurrence relations, and after that we'll get into generating functions. So take a moment, pause the video, and think about this first problem. How many binary strings are there of length n with the property that every one is followed by a 0? So if you took a moment to think about it, you really only have our current existing counting methods to try to solve this problem. May have turned out to be a bit of a challenge, and the idea is that with recurrence relations we can look at this in a different light with a different viewpoint and see that it'll be slightly more straightforward to count it with another technique. So that's our motivating problem. We'll get to it at the end of the lecture. So let's get to our first example. So the Fibonacci sequence is the sequence given by 1, 1, 2, 3, 5, 8, and so on. And what does the and so on mean? It means that the sequence is generated by this relationship, that each term is the sum of the previous two terms. So for example, this is our first term, f sub 1. This is our second term, f sub 2. And so the relationship that's written here tells us that f sub 3 is equal to f sub 2 plus f sub 1. So that means the third term would be the sum of the previous two. The fourth term is the sum of the previous two, and so on for the fifth, the sixth, and what about the seventh term? The seventh term would be the sum of the previous two, which has a value of 13. So that's what this relationship is telling us. It's telling us how to get the next term of the sequence from the previous two terms. That alone doesn't determine the sequence. We had to have a starting point. So there we had to start our sequence off, in this case with two ones, and that's what we have written here. These are our initial values. So this equation that relates a term of a sequence to prior terms in the sequence, this is known as a recurrence relation. A recurrence relation, and that's our topic of study here. So the idea is once we have a recurrence relation and the first however many terms, we'll have to discuss that later on how many we need, so we have in this case the first two terms, then that's enough to define the sequence of numbers. So our whole goal in this case is we are interested in sequences of numbers, and we are describing that sequence of numbers by the nth term of the sequence is obtained from prior terms in the sequence. And so in this case, our first term is 1, our second term is 1, and then we can use the recurrence relation to get subsequent terms after that. F sub 3 is f sub 2 plus f sub 1, which is 1 plus 1 or 2. F sub 4 is f sub 3 plus f sub 2, which is 2 plus 1, which is 3, and so on. These were our initial values. And then the subsequent terms we got by using the recurrence relation. In the first case we took n equal to 2, and then we took n equal to 3, and so on to generate the sequence. So let's have a look at another example. In this example we aren't given a recurrence relation, but we are given a sequence that we are trying to determine. In this case our sequence is little b sub n, and it's the number of binary strings of length n. Now we already know how to determine b sub n. This is one of our fundamental counting objects, so binary strings. So the idea is if we have a string of length n, so in other words there's n spots that we're going to fill with bits. So there's two choices for that first bit, there are two choices for the second bit, and so on down the line. We've got two choices all the way down the line. So if this is our string and our bit number is indicated here, this is just so I can keep track of how many bits there are, then we know that by the rule of product, the number of binary strings of length n is two choices for each bit. There are n bits in total, so it's 2 to the n. However, what I want to do is I want to look at a new way to count these. In other words, I want to look at this sequence b sub n and try to figure out a relationship between terms in that sequence. How is one term related to other terms in that sequence? So how would the number of binary strings of length 8 be related to binary strings of smaller length? That's our new way, our new approach. Now typically we wouldn't do this because we already have such a straightforward way to count this particular object. But if we are thinking about maybe not just counting, but maybe generating binary strings, this would be a very natural way to generate them. How do I generate all the binary strings of length 5? I would generate all the ones of length 4 and then put an extra bit on the end to generate more strings of the longer length. And so that's our idea here. To construct a binary string of length n, we first construct one of length n minus 1 bits. So again, we'll draw our picture of our binary string with the spots we need to fill. So we've got our binary string of length n here. The way we built it up is a binary string of length n minus 1, and then one extra bit we add on the end. So how many strings are there of length n? Well, let's think about counting them. How many ways are there to fill these slots? Well, those spots can be filled in, again, we're not thinking about the way we counted above, we're thinking about in terms of breaking it down to smaller length strings. So there are b sub n minus 1 choices to fill those slots, because that's how many binary strings there are of length n minus 1. And then I've got 2 choices for a bit to append on the end of it. And so what that means is that the number of binary strings of length n, that is just the number of binary strings there are of length n minus 1, and then 2 choices to append that extra bit, so it's 2 times bn minus 1. And this is for n bigger than or equal to 2. It doesn't help us in the very first case. So in the first case, we are interested in how many strings are there of length 1, and there are 2, either a 0 or a 1. And so there is our new way of determining the number of binary strings of length n. Here we did it in a recursive way. We built up binary strings of length n by binary strings of length n minus 1. And we can see from this that from this recurrence relation and the initial value, we can compute bn for various n. So in particular, b sub 1 is 2. What is b sub 2? b sub 2 is twice b sub 1, so that would be 4. b sub 3 is twice b sub 2, so that would be 8. And b sub 4 is twice b sub 3, which is 16, and so on. So we've got a recurrence relation, so a relationship between one element of the sequence and prior elements of the sequence. And with the initial condition, we're able to generate the terms of the sequence. And then from these patterns, perhaps we could, at this point, conjecture or guess that, hey, b to the n looks like it's 2 to the power of n. That would be an example of solving the recurrence relation. Once we had a recurrence relation that generates a sequence, we will be asking the subsequent question, what is the solution? How can we write down an expression for b sub n just in terms of n alone? So in other words, how could I find the 10th term without having to know the prior 9 terms? Could I get a formula that gives it to me right away? And the idea is, yeah, we can, and in this case we get the value of 2 to the n. So we set up our recurrence relation, and then later on in this section on recurrence relations we'll learn how to solve them. So how about another example? Again, right now we're just getting practice with how recurrence relations can come up in counting problems. So we're looking at problems we already know how to solve, at least problems we know how to count using our elementary techniques. So let Kn be the number of edges in the complete graph on n vertices. Let's come up with a recurrence relation for k sub n, little k sub n. We already know what the value is. We already know it's going to be n choose 2. That was our basic counting techniques. For every 2 vertices, there's an edge between them, so it's just a number of ways to choose 2 vertices from n. But we're going to use this as a motivation for trying to think about how to take a problem involving n vertices and break it down into a problem involving fewer vertices. To just get a feel for what little k sub n is, let's just list a few things. So we're going to list k sub 1. It's a complete graph on one vertex. It has no edges, so little k sub 1 is 0. What is k sub 2? So big k sub 2 is a complete graph on 2 vertices. There is what it looks like. It has one edge. What is big k sub 3? That's our graph, and so it has 3 edges. And maybe one more. We'll go k sub 4. It looks like this, and therefore it has 6 edges. And that's the sequence we're interested in. We are interested in this sequence here as it continues on. What is k sub n for any n? We already know the answer, as I said. It's just n choose 2, but we're trying to use this as a motivating example to think about another way to count these kinds of objects. So here's the other way to count them. Let's think about k sub n minus 1, the complete graph on n minus 1 vertices. So it looks like this. There's our n minus 1 vertices, and then we've got edges that connect everything. And then 2 would connect to everything as well. And then 3 would connect to everything as well. And so on down the line. So there's our k sub n minus 1. Now how do we build k sub n from that? Well, k sub n is going to be the bigger graph, where we add one new vertex. I'll label it n. And then we add a bunch of new edges. How many edges do we add? Well, we add one new edge for every vertex existing in k sub n minus 1. So we've just added n minus 1 edges. So we started with k sub n minus 1. We popped in a new vertex n, and then n minus 1 edges. So what does that mean? So that means that we can get a count for how many edges there are in k sub n. So let's just make a few notes. There are k sub n minus 1 edges in k sub n minus 1. And we add n minus 1 edges to get k sub n. So what that means is the number of edges in k sub n is the number of edges in k sub n minus 1 plus the n minus 1 edges we've just added. And so there's our recurrence relation. That's for n bigger than or equal to 2. And we have our initial condition that says if we had a graph with only one vertex, there are no edges for it. And so there we go. We've got our recurrence relation and our initial condition, or our initial value. So this is our what we call a recurrence relation for the sequence of edge counts and our initial value. Now those two bits of information are enough to determine the sequence. So we could generate the values k sub n from those two bits of information. We got k sub 1 is 0. What is k sub 2? Well, k sub 2 is k sub 1 plus 1. That's what the recurrence relation is telling us. So it's 0 plus 1 or 1. What is k sub 3? The recurrence relation tells us it's the previous value plus the two new edges we add. K sub 2 is 1, so we get 1 plus 2 is 3. And maybe we'll finish on the last one, k sub 4. That is k sub 3 plus the 3 new edges we're going to add. And so that's 6. And we keep going. And we see that the values we've got here, actually there's even one more over on the side, so the values we got here are precisely the values we got by listing the actual graphs out and counting. And so that's the idea, is we've attacked this problem by, instead of being interested in just, what is the number of edges for a particular complete graph, instead we thought about the sequence. What is this sequence little k sub n, and how are the terms of this sequence related to each other? That's the recurrence relation. And once we come up with this relationship and we start off our values somewhere, in this case k of 1 is 0, then we can use the recurrence relation to generate the other values of the sequence. And so that brings us to our definition. A linear recurrence relation of order k with constant coefficients for a sequence. So that's the underlying object here, is there is a sequence, and a recurrence relation for that sequence is an equation that relates the terms of the sequence. In this case, it's relating one term to the k previous terms. So we're relating the nth term to the previous k terms. And this is known as a kth order or an order k recurrence relation, because it's relating a term of the sequence to the k previous ones. We don't have to use all k previous ones. It could just relate the nth term with the nth minus k term. All of these c's in between could be 0, and it could just be a relationship like that. The only thing we must have necessarily is that c0 is non-zero and ck is non-zero. So it's got to relate the nth term to some prior term. And the prior term that's furthest away, that gives us the order. In this case, it's k away. This equation could involve some function of n in it. If the function of n is 0, we say the relation is homogeneous. If it's non-zero, we say it's non-homogeneous. So let's go back and look at our examples. So we had example 4.2. In that case, it was our binary sequences example. We had our recurrence relation that said b sub n is 2 times bn minus 1. And I won't write the initial condition or the n value because I'm just focusing on the recurrence relation here. But we could write it as b sub n minus 2bn minus 1 is equal to 0. And then comparing that with the statement of the definition, this tells us it's a first order. Why is it a first order? Well, again, remember the order is just for whatever term you're at, how many terms prior are you using? And in this case, it's using up to just one term prior. So that's the first order. We only need to go back one term and use that to generate the next term. So it's first order. We've got a 0 on the right-hand side, so it's homogeneous. And it's a recurrence relation. So we call that a first order homogeneous recurrence relation. What about example 4.3? This was our edges in a complete graph. There we had k sub n is equal to k sub n minus 1 plus n minus 1. If we rearrange it a little bit, we move all of the terms of the sequence to one side and anything else to the other side. Then we get this expression. Again, this is first order because it just uses the one prior term. So it's a first order and it's non-homogeneous. It's non-homogeneous because it doesn't have a 0 there. It's got a non-zero function of n. What about the last example, which actually ended up being our first example, the Fibonacci sequence. So in this case, this was f of n plus 1 is equal to f of n plus f of n minus 1. We could rewrite this as f sub n plus 1 minus f sub n minus f sub n minus 1 is equal to 0. What order is it? Well, whatever term I'm interested in, I have to go as far back as 2 before it. So that tells me that it's a second order. Second order, and in this case it's homogeneous because of the 0 there, recurrence relation. And so there's just our previous examples now connected with the definition of a recurrence relation. So there's our formal definition of a recurrence relation. And the order, again, is just how far back you have to go in the sequence to generate the next term of the sequence. Let's have a look at some notes. So there's a note about subscripts here, and it's just because when I write down various recurrence relations, sometimes I'll write the Fibonacci one in this way. I'll write it as f sub n is equal to f sub n minus 1 plus f sub n minus 2. And sometimes this causes a point of confusion because the subscripts have changed. But really, these are saying the same thing. All it's saying is that to get a term of the Fibonacci sequence, I just have to add the prior to. And either one of the equations is saying that exact same thing. To get a term of the sequence, add the prior to. So we just have to be careful not to, put too much emphasis on these subscripts. It's more about the relationship between the subscripts. So all of these say the same thing. These all say the same thing. What do they say? Well, for example, they all say that if I wanted to find the 5th term of the sequence, think about what they're all telling you. If I wanted to find the 5th term, well, this one is saying to find the 5th term, so I would take n as 4. It would say to find the 5th term, I would take 2 times a sub 4 plus 4. What would this one say? This would say a sub 5. That would be 2 times a sub 4 plus 4. What about this one? A sub 5, so that would be n is equal to 3. That would say 2 times a sub 4 plus 4. So they all say the same thing. They all say just take twice the previous one and add the subscript of the previous one. The other comment is about initial values. What the initial values do is they allow us to fix the terms of the sequence. The relation itself just tells us how to generate the next term from prior terms. The initial values tell us how to start off the sequence. So to fix the values, in other words, to produce a unique set of values that satisfy the recurrence relation. So to fix the values of a recurrence relation of order k, we need k consecutive initial values. So we need k values in order, and then we can start producing the rest of the terms of the sequence. So for example, let's look at the Fibonacci sequence. So f sub n is f sub n minus 1 plus f sub n minus 2. We could use f sub 1 and f sub 2. We could take both of those to be 1. That would be one set of initial conditions we could use. And they would generate the sequence 1, 1, 2, 3, and so on. Or we could use f sub 2 equals 1, f sub 3 equals 2. That would produce the same sequence. Or we could use f sub 3 equals 2 and f sub 4 equals 3. Or we could even go back a little bit. We could say f of 0 is 0 and f sub 1 is 1. So as long as we had 2 consecutive values, we can get the rest in the sequence. Why is this the case? Well, let's just focus on one. I will focus on, let's say we have these 2 consecutive values. So that means here's my sequence, 1, 2, 3, 4, and so on. I know that f of 3 and f of 4 that's 2 and that's 3. So maybe I won't do the and so on yet. I will put a few more terms in here. Then knowing those two consecutive values and the relationship between the terms of the sequence, we can get the rest of them. We can go 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. We could also go backwards. We could say, what has to be put here? Well, whatever is put here, when I add 2 to it, I've got to get the value of 3. So that tells me that that's got to be a 1. And what has to go in the 1 spot? Well, whatever is put there, when I add it to 1, it's got to add to 2. So that's also got to be a 1. And we can even back it up further. We could say, what would the 0th term be? Well, whatever I put in the 0 spot, when I add it to 1, has to give me 1. So this could be a 0. So this sequence is filled out uniquely once I've identified 2 consecutive terms. Then I can take those 2 consecutive terms and generate the rest of the sequence, both before and after it, using the recurrence relation. All right, let's have a look at some examples. Now we'll come back to that first motivating problem, the set of binary strings of length n with the property that every one is followed by a 0. So that's what we're going to call our set S sub n. So the first question says, let's get a feel for these sets for various values of n. What is S sub 1? What is S sub 2? And I've on purpose left a gap here because I'm going to fill something in this spot. So in your notes you can leave a gap there as well. So what is S sub 1? So those are the strings of length 1 for which every 1, if it appears, has to be followed by a 0. So this means I can't have a 1 in a string of length 1 because by necessity, if I had a 1, I'd have to have a 0 following it. So the length would have to be 2 or more. So there's only one string of length 1, and that's that string there. How about the strings of length 2? Well, let's think about how they could start. They could start with a 0, but then it couldn't end in a 1 because of the condition that every 1 is followed by a 0, so it'd have to end in a 0. On the other hand, it could start with a 1, but if it starts with a 1, it has to be immediately followed by a 0, and there we've used up our 2 spots. So those are the only 2 strings we have. What about S3? Well, again, it could start with a 0. The next term could be a 0, and then the last term has to be a 0. Or it could be a 0. The next term could be a 1, but if it's a 1, then the next term is followed by a 0. And that exhausts all possibilities that start with a 0. What about if it started with a 1? Well, if it started with a 1, the next term would have to be a 0. And then the last term, it has to be a 0 as well, because we can't end in a 1. So there's all our strings of length 3. So what we have is that, question 2 says let C sub n be the size of these sets. So C sub 1 in this case would be 1, C sub 2 would be 2, and C sub 3 would be 3. Now let's go ahead and look at what question 2 is asking. Question 2 is now saying, let's come up with a recurrence relation for C sub n. So C sub n will form this sequence of values, which are sizes of these sets, big S sub n. How are the C sub n's related to each other? Well, what can we use? Well, what we'll note is that any string in S sub n has one of the following forms. Now, before I write down what I'm about to write down, a lot of times I get asked the question, how do we know to do this step next? Well, again, the idea is we're looking for a recurrence relation. So what that means is we are going to have to try to find a relationship between C sub n and its immediate predecessors, so the things right before it, c sub n minus 1, maybe c sub n minus 2, etc. Another way to phrase that is we are trying to find a relationship between elements in the set S sub n and the strings that are of length 1 less or 2 less, and so on. So the elements of Sn minus 1 or Sn minus 2. So I'm looking for this relationship, how to get a string of length n from its immediate predecessors, the strings of shorter length. So when I think about this, what does a string of Sn have to look like? Well, it could start with a 0. If it started with a 0, then after that, we would get a string of length n minus 1, and that string of length n minus 1 still has to satisfy the property that every one is followed by a 0. So this u represents a string in S sub n minus 1. So that's what our string in Sn has to look like if it's going to start with a 0. It'll be 0 and then followed by a string of length n minus 1 with that given property. 1 is followed by a 0. Or our string is going to start with a 1, in which case it must immediately be followed by a 0. And then after that, it could be a string of length n minus 2, where every time a 1 appears, it's followed by a 0. And so those are the two cases that we have. Now from these two cases, what we get is that, now typically I won't write down these sets, but I will in this example. I won't in the next one because we'll jump right to the counts. But the idea is that what we've just established is that the set S sub n, we've just written it as a disjoint union. It's 0 appended to the front of any element of S sub n minus 1. So I'm using this notation 0 in front of the set, meaning that just take 0 and append it to the front of any element of the set S sub n minus 1. Union 1, 0 appended to the front of any element of S sub n minus 2. And this is a disjoint union. So what that means is if I go to take the size of these sets, it's just the sum of the size of these sets. But what is the size of 0 appended to the front of any element of S sub n minus 1? Well, all we did was just take all of S sub n minus 1 and stick a 0 in front of every element. So we haven't changed the size of that set. So it's still equal to the size of that, plus, and again, what did we get for the next set? We just took all of S sub n minus 2 and just stuck a 1, 0 in front of it. And so we didn't change the number of elements in the set. And so what that gives us is Cn is equal to Cn minus 1 plus Cn minus 2. And so there's our recurrence relation. This is for n bigger than or equal to 3. And it tells us that to get the next term of the sequence, so the number of binary strings of length n, we just need to know the number of binary strings of length n minus 1 and n minus 2 and add them together. If we wanted to know some initial conditions, well, this is of order 2, so we need 2 initial conditions. So I got C1 is equal to 1, C2 is equal to 2, and there's our recurrence relation with initial values that generate our sequence. So notice that this is essentially the Fibonacci sequence. And we can use these now to generate the terms of our sequence. C sub 1 is 1, C sub 2 is 2, and then to get the next term of our sequence it would be 3, 2 plus 3 is 5, then 8, then 13, then 21, and so on. And which terms are these? This would be the first term, the second term, the third term, the fourth term, the fifth term, the sixth term, the seventh term. So for example, if I'm interested in the number of binary strings of length 7, where every one is followed by a 0, I know that there are 21 such strings. So that's how we can use this idea of a recurrence relation to solve counting problems. Ultimately, our goal in the next few lectures will be to take a recurrence relation like we just got at the end and come up with a way to find a formula for C sub n, find some closed form. So C sub n is some function of n in this case, and see if we can write down an expression so that we don't have to work out all prior terms of the sequence to get the nth term. We can get it immediately from a formula. So that's the idea of what we call solving a recurrence relation. Now, I did leave a gap up here, and I just wanted to mention at this point what we can put into that gap. You may have guessed at this point what I might want to put there. It's going to be an S sub something. Now, when I do this example, I'm often asked about the question, what about binary strings of length 0? And the question that usually follows is there a binary string of length 0 with the property that every one is followed by a 0? How many are there? Is there one? Is there none? What is it? Well, this is really a question about the empty string. And the empty string is a string. It's got no characters in it, so there really is a string. You can maybe put it with a couple of quotes with empty space between them. So that's our empty string, and that lives there. So in this case, C sub 0 would be 1. So this is trying to answer the question of what would S sub 0 be? Do we consider an empty string? Do we not consider an empty string? And you can see that once we've done all the work for our recurrence relation, that there's a natural suggestion that says, yeah, you definitely want to consider the empty string. Why is that? Well, just think about going backwards. Whatever number is here, we want it to have the property that it satisfies the recurrence relation. So when I add it to that number, should give me that number. And so that suggests that that should be a 1 there. Moreover, the construction that we went through actually tells us that we want to consider the empty string there. Because if we think about how we built up these strings here, the way we did it was we took the prior string and we just inserted a 0 in front of it. So that gave us this first one here, where that came from there, and then we just appended a 0 in front. Now, how did we get the other string? The one that started with the 1. Well, it started with a 1, 0. So the way we got that was we took the empty string and we appended in front of it the 1, 0. So this was really a 1, 0 followed by the empty string, which is just 1, 0. And so our construction even tells us that we'd want to consider the empty string in these cases as well. And the empty string, as computing science students, you probably are well aware, is an object that you do have in your computing languages. So you do have this notion of an empty string. So it's certainly a string that we want to include in our counts. Now we can also see that as we go on, we can use our construction to get the next terms or the next strings in our sequence. So, for example, I want to get these 3. Where did those ones come from? Well, all the ones that started with 0 came from these ones where I appended a 0 to the front of them. So that gave me my 0, 0, 0 and my 0, 1, 0. So those were where those two came from. And that's this part right here. I appended a 0 to the front of the elements of the prior set. But then I also got the ones that start with 1. Where did those come from? That involved going back 2 sets, way back to here, and then appending in front of that one a 1, 0 in front of it. So there's the 1, 0 appended in front of the 0 from 2 sets ago. And so that was this portion. And so these are the specifics of the construction that I gave more generally down here. Those are them as actually applied to these sets. So if you wanted to generate S sub 4, you actually have a mechanism for doing that now. You just append a 0 to the front of these ones and a 1, 0 to the front of these ones, and now you've got all your elements of S sub 4. So not only do we have a way of counting them through this recurrence relation, we also have a way of generating them recursively. So we have a recursive process for generating these binary strings. So that's one of the powers with this approach. We get a method for generating the objects as well as counting them. So let's have a look at the last example. Let d sub n be the set of all strings of length n over the alphabet A, B, C, D, such that, we have a couple of conditions we want to satisfy. Every A is followed by a C, and every B is followed by two D's. So if there's an A appearing, it's got to be of the form AC, and if a B appears, it has to be a BDD. So let's list these sets, D0, D1, and D2, just so we get a feel for what these sets are. Also, we can get a feel for how to generate the next one, which is going to help in coming up with a recurrence relation. D sub 0, strings of length 0, there's only one, the empty string. Strings of length 1. Well, let's go alphabetically. Can it start with an A? No, because if it starts with an A, it has to have a C that follows it, so now it's no longer of length 1. Could it start with a B? No, if it starts with a B, it'd have to be followed by two D's, and so it's no longer of length 1. Could it start with a C? Sure. Could it start with a D? Absolutely. So there's our two choices. How about D sub 2? Could it start with an A? Yep, because it's followed by a C, and then that would eat up the two spots. Could it start with a B? Nope, because it would have to be BDD, which is of length 3. How about, can it start with a C? Sure, it could start with a C, and then what follows it has to be either a C or a D, so it could go CC or CD. What about if it starts with a D? Sure, it could go DC or DD. And so there's all our options. So what we have is D sub 0 is 1, D sub 1 is 2, and D sub 2 is 5. So here I've dipped a bit into question 2, which says let little d sub n be the size of the set D sub n. So now we've got these first three terms of our sequence. We're interested in finding a recurrence relation for D sub n. Now you can kind of think of how I started to build this. I was kind of thinking about what does it start with and how to go from there. So can it start with an A? Can it start with a B? Can it start with a C? So that's what we're going to do. We're going to think about these different cases. So a string in Dn has one of the following forms. So what must it look like? Well, it could start with an A. If it starts with an A, it'd have to be immediately followed by a C. And then after that, it's made up of a word where that word still has to satisfy the conditions, but now it's of length n minus 2. So that word is an element of Dn minus 2. Or it could start with a B. If it starts with a B, it would have to go BDD and then end in a word that still satisfies the conditions, but is of length n minus 3. So that word U has to be in Dn minus 3. Or it could start with a C, and then there really are no other conditions other than that it has to end in a word of length n minus 1 that satisfies the original properties. So where U is an element of Dn minus 1. Or it could start with a D, be followed by a word U of length n minus 1. So those are our 4 possible cases we have for what the form of a word in D sub n looks like. And so from this, we know that how many words are there going to be of length n? Well, I'm going to see if we can get them in order now. There's going to be the ones that depend on or are built from words of length 1 less by appending a C or D to the front of them. So of the Dn minus 1 words of length n minus 1, we could stick a C or a D in front of them. So I can produce, for any one of those, I can produce 2 different options for words of length n. Put a C in front of it or put a D in front of it. I could also generate them from the words of length n minus 2. And for those, I just stick an AC in front of them. And I could also generate them from the words of length n minus 3. I would just stick a BDD in front of them. And so there is my recurrence relation that says the number of words of length n is just twice the number of words of length n minus 1 plus the words of length n minus 2 plus the words of length n minus 3. And then we can also throw in our initial values. How many initial values do I need? Well, I've just expressed the nth term in terms of the prior 3. And so I've had to go back 3 terms. And so that tells me that I would need 3 initial conditions. D0 is 1, D1 is 2, and D2 is 5. And so there we go. And we can get then that n is greater than or equal to 3. That's how we can get the d sub 3 or higher. And so we've got our recurrence relation and we've got our initial values. And so we could use those. We could say, how many strings are there of length 3? How about of length 4? How about of length 5? We can just start generating those sequences of values and get whichever value we want. As I said before, though, our ultimate goal with this is to try to come up with an expression for little d sub n entirely in terms of just n alone, so we can pop in, if I wanted to know what d sub 100 was, I don't want to have to work out the first 99 terms and then use the recurrence relation on the prior 3 to get the 100th term. I'd like to have a formula that I can just pop n equals 100 in and get the value for d sub 100 out. That's our ultimate goal, solving the recurrence relation for a closed formula for d sub n. But for right now, we're just getting practice with generating recurrence relations to see how they can come up in counting problems. All right, thanks very much for watching, and we'll see you in the next lecture.